Yeah, it should be. Hi. So, hello everybody, and welcome to this morning session where we're going to talk about soft matter in space. And to open this session, we have a talk by Anina from Université Paris-Saclay. Please, Anina.
Okay, great. So I'm delighted to be here to talk to you about the results from our project on the coarsening of foams, so the Foam C project. So the project has been coordinated by, and is coordinated by Dominique Langerin, and so I'm Nina Salonen, and I'm talking on behalf of my colleagues on the results we've had. So we're thinking about coarsening. So of course, coarsening, it's a process that you might observe in many material processes, in biological systems, but today we're going to be thinking about foams in particular. So if we look at, we're going to immediately start thinking about what are the motivations, what are the questions we're asking in the project to look about foams. So once we make a foam, we make an aqueous foam, it will start to evolve. So the bubble size will grow and the liquid will flow out of it because of gravitational drainage or evaporation. And so what we end up very quickly is a very inhomogeneous foam. And so to understand the aging mechanisms, we need to be able to isolate them. And so we can get rid of coalescence with an efficient stabilizer. We can seal our systems to properly and get rid of evaporation. But of course, drainage is why we need to go into microgravity because we can't index match, or density match our foams. Can't really index match them either, but that's not the problem today. So we can isolate coarsening in our microgravity experiments, and so the idea of the project is to understand the underlying physics of the coarsening of foams. So I'll start by showing you what coarsening looks like. So this is a video taken by Chiara Guidolin, a student in our group, used to be a student in our group, looking at the coarsening of a single layer of bubbles. So what you see here in black are bubbles, and in white you see the liquid around them. And so as you can see in our foam, it's the bubble size on average is growing, it's jiggling around as the bubbles rearrange to relax into their structures. So what's driving the coarsening is the differences in the Laplace pressure. So in the smaller bubbles, the pressure is higher than in the larger ones. And so what we have, this results in gas diffusion from the smaller to the bigger bubbles, the growth of the average bubble size, and relaxation of the bubble, of the structure through rearrangements. So an important parameter in understanding coarsening and in understanding foam structure is the liquid fraction. So here you see drawings of at varying liquid fractions. So epsilon is liquid fraction. It's the volume of liquid over the total volume of our foam. And so what we see on the very left is a very dry foam. So in a very dry foam, we have these polyhedral bubbles with films in between. As the volume fraction of liquid increases, we go to less and less compressed bubbles with smaller films until we lose the films completely, and we end up with a suspension of bubbles. So what we know about coarsening is we know very well what happens in the very dry limits. We have a power law coarsening with a 1/2 power law. In the very wet foams, we also have a power law with a 1/3 coarsening. So the power law coarsening has been theoretically predicted and experimentally verified in the case of these two limits. And what we also have is a self-similar foam structure during the coarsening process. However, what we don't know, or what we didn't know about before the project, was really what happens in between. What happens with these wet foams where we're not completely dry and the bubbles are not completely disconnected. So that the question of foam C was to say, how do these foams coarsen? And so some of the questions were, what are the coarsening laws in wet foams? How do you go from 1/2 to 1/3 power law? What happens to bubble rearrangements? How do they stop? Do they become scarcer? And how does the physical chemistry of the systems explain the coarsening? So carry out the experiments, we're working on the soft matter dynamics unit. So here you'd see a schematic of the experiment. And so what I want you to remember from today is that it's in here, what we can do is we have a carousel with 20 sample holders. So we can have 20 samples being measured partially in parallel. So this allows us to do really long runs. And we also do the foam generation and diagnostics, of course, in here. So we have the soft matter dynamics unit. We have varying different onboard diagnostics. And so these diagnostics allow us to follow the average bubble size, the bubble size distribution, the bubble displacements, and the bubble rearrangements in our foams as a function of time. So those are what we can measure. And we measure them in these foam cells. So here, a photograph of the foam cells, which are around 5 centimeters high. You have a small 1 centimeter, the foam cubic, measuring the foam, where the foam is generated and where it evolves. So we generate the foams in there, typically at a 1 hertz frequency, a magnetic piston, which goes up and down to shake our foams, to make the foam. So during 2 minutes, you shake it. And so what we've looked at are 68 different samples of varying liquid fractions, going from 15, reasonably dry, 15%, to very wet, 50% liquid fraction foams. And we've also varied the solution chemistry. So most of the systems that I'll show you were with a classical stable surfactant, so a cationic surfactant above the CMC, but we've also looked at varying things by looking at the role of micelles, so having no micelles, looking at the impact of the rigidity of the interfaces, the surface rheology, looking at the bulk rheology, making more viscous fluids, looking at the kinetics of adsorption of the molecules to and fro with a polymeric stabilizer, looking at very thin films or proteins. So what does it look like? So here I show you 2 videos of the foam coarsening process. One with both are over 24 hours. So this on the left, it's the 15% liquid fraction. On the right, we have the 40% liquid fraction. So you see the rate of coarsening is very different in both. So these are the images. So across, it's around 1 centimeter across. And so you see reasonably good statistics in the beginning, so we have a lot of bubbles to get good bubble sizes, and of course we stop the experiments as soon as we start getting just a few bubbles. So the coarsening rates change, so from these images we can treat the images to get the average bubble size to look at the evolution in time, and so here what I've plotted is the average bubble size as a function of time. So what we see is the 15% in black with a 1/2 power law, as we'd expect for these dry foams going through films. In yellow, the 50% liquid fraction, where the coarsening is through the bulk phase of these disconnected bubbles. And in between, we have what's surprising is that we have very sharp transition from one to the other. And another thing about the transition, it's around 42% liquid fraction, so it's really wet. So it's well beyond the random close packing of what we'd expect. So with our polydispersities, the random close packing, it's around 31%. So,
what's the 32? Your y-axis is R32.
Sorry, it's the sorter radius. So the surface weighted radius of the bubbles. So basically, we're weighted more by the area of the bubbles. So the bigger ones count, of course, a bit more than the tiny ones. So, but it's one of the averages of the radius. So it's the average radius function of time. So what we see is this very shifted transition, which is very sharp. And so the question is, why do we measure these film coarsening at very high liquid fractions? So of course, it suggests that we have films. And this is indeed the case. And so what we see, if we look at the photograph of some bubbles, they stick together. So what we see is that instead of having our bubbles that will unstick at higher volume fractions, they will stick together and they will have a contact angle, so an attraction between them. So we can see this if we look at the coarsening rates as a function of liquid fraction. So we see coarse adhesive foams up to around, so the film-dominated coarsening up to about 40%. So what this also says that if we have films, the transfer through films is much more efficient, and we see and the coarsening through the films dominates, giving us a 1/2 power law. Another thing that we observed in these systems is if we look at the distributions. So here we can look at, so this is now the probability distribution function of finding a bubble of a given radius. So here the radius is normalized by the average radius. And so what we see in yellow is what we have in the beginning, kind of a distribution with no specific a not very peaked one, but what we were surprised by is seeing that in time you develop this really very strong peak at very small bubble sizes. And this is something that we saw in all of our dryer foams, and this is in fact ends up being the steady state bubble size distribution. So there's an existence of these very small bubbles that persist for much longer than what people had seen previously. So what are these small bubbles? So in fact, what they are is, if we look at this photo, they're these tiny bubbles that dissociate from the global foam network, and so they end up having less neighbors than their others because they're not connected from all sides, and so their coarsening becomes slower, and so they remain for much, much longer in our structures. So we kind of saw the existence of these roaming bubbles in our systems. So that was looking at the bubble size distributions. So I'm giving you a few highlights. So getting now to the results on the varying stabilizer chemistry. So what we looked at is, again, so this again, the average radius as a function of time with our different solutions. So what we see is that we can have more than a 10-fold difference in the rate of coarsening by choosing the chemistry of our systems. So the power laws are the same here at 30% liquid fraction, but the coarsening is different. So how can we understand why it's different? So what fixes the coarsening rate is, if we now go back to looking at the rates of coarsening, so we have the evolution of the radius as a square root of time, and omega is our coarsening rate. So omega, it depends on the surface tension and the permeability of the films, the pressure, and F, the function, the area of the films. So what's nice is that this kappa, this permeability, we can measure independently on ground. So we can do ground-based experiments where we just measure kappa for a given surfactant solution. So these what are called omega 0. And so we can compare, check if it's actually the permeability and the surface tension that control the coarsening in different physical chemistries. And if we plot the two omegas as a function of another, we see that we have very nice linear relationships. So this shows that in the 30% liquid fraction, the coarsening is really controlled by the permeability of the films and the surface tension. So we can ask, so does this hold at all liquid fractions? And if I'm asking the question, it's of course it doesn't. And so what we can do here is plot basically the ratio of the two. So here you see the points at 30%, they're reasonably collapsed. What we see is that in the drier foams at lower liquid fractions, all the data are all together. So this is because the foam structures are very similar. So the structure of the foam is dominated by the osmotic pressure, which sets the film size. However, they become different at higher liquid fractions. And so I'll just point out these two, the blue and the orange points. So why are they different? So we can understand the blue points because this is the C12G2 that has very strong adhesion. So here, the structure of the foam is different because the attraction is much stronger. So we have bigger films up to higher liquid fractions, and hence the transfer is faster than we'd expect. Orange sample, and we have it's not, the attraction is not stronger between the bubbles, but we have really dense surface layers. So here, what we propose is that the time to get for the gas to go out of the bubble to go through the surfactant film is the rate limiting process. And so this means that we also have some transfer through the thicker regions, the bulk phase, and so we have a coarsening that's faster than we'd expect just from assuming the same structures in the other ones. So we can say that the permeability and surface tension, they suffice at low liquid fractions, but not at higher ones. So this brings me to my conclusions. 5 minutes, okay, so I have plenty of time. Including questions, no, but it's perfect. So I can say that we have successful experiments. We've been really happy with how things were running. The data we have, we've shown a sharp transition in the coarsening power laws of the wet foams. We've shown the existence of roaming bubbles, and we've explored the impact of solution chemistry on the coarsening process. So what's still to come, there's a lot of data, and so we'll see if... So you saw the videos, the bubbles are jiggling around. So the question is, how does the bubble dynamics, how is this evolve as the liquid fraction is changing? So we're still treating the images, also treating the scattering data. And with that, that was the video that you saw already. And with that, I leave you again with the collaborators from the project. Thank you.
Matthias Sperl from Cologne. I have a question when you compare the overall results you get from the space station with another microgravity system that was done in Constance with the levitation. So what are the principal differences? Because they also end up with some power laws that you presented very prominently.
Yeah, so the experiment that they did in Constance was basically surfactant foams with a magnetic levitation, and so what they saw was a rather gradual transition from one power law to another. So I think there, what's complicated is that the in magnetic levitation, keeping in the wettest foams having a very homogeneous liquid fraction is not very simple, and keeping it up for very long periods of time is also complicated. So I think there, and they also had a different system. So they had slightly differing results from ours, and so there I think it's not so easy to counteract gravity on the ground. So I think there's possibly some bias in those experiments, but they were very nice experiments to really show how towards the kind of slightly wetter than the driest foams to see the persistence of the evolution.
Right, do you have another question?
I'm Alberto Vailati, University of Milan, and I apologize, but I have a very naive question. In the introduction, you mentioned the wet foams, and I was wondering whether in the dynamic of coarsening there was any relation with spinodal decomposition, any formal relation with spinodal decomposition, because the process bears some similarities.
Yes. So I mean, there you have they're both. The coarsening process. I mean, the coarsening processes with the domain size that's growing. So I think in this case you have there's a definite similarity in the two, but the formal I'm not sure now if there's a formal relationship between them. I don't think so.
Thanks. Luigi Cristofolini, University of Parma, Italy. Thanks, very nice results and nice presentation. I have a question about polydispersity. You mentioned, you showed all the graphs normalized to the average radius, and my experience is on emulsions, and in that case, I'm sure it's really a big issue. You cannot characterize completely the wide polydispersity by a single technique. So I wonder if in the case of foams, life is simpler, and you can rely completely on what you see on the microscope on overview camera, or if you have the possibility to have smaller drops that will grow eventually in time and appear.
Okay, so what's I mean, what's nice in what helps us with the foams is that we have the solubility tends to be quite large of the gas, and also the surface tension is high. So in general, the kind of tiny bubbles, we don't see tiny bubbles that nucleate from the solution in time and then appear. So globally, the smallest bubbles, we catch even the smallest bubbles. So we make the bubbles as we're whisking it, and the smallest bubbles we have, rather in the beginning of the experiment, as we're measuring, they're slightly small to properly measure them with the automatic scripts that we use, but we can kind of catch them by hand. So right in the beginning, we might lose some, but we don't treat these ones. We just stick to the ones later on. So I think we have all of them with the camera.
Okay, maybe one last very small question until we move on to the next speaker. Yeah.
Good morning, I'm Stefano Buzzaccaro from Politecnico of Milan. I have a question. Your result is related to the imaging part of your setup.
Yeah.
Do you expect some different analyzing the bulk of the bubble in the bulk?
So what I didn't show is what we did in the beginning was we also analyzed the transmission. So we did look at the average bubble size. We also compare with the transmitted radius. So this compares perfectly with the average that we obtained from the overview images. On the dynamics, we're currently comparing the treating the images from the surface from the signals that we get from the bulk, from the scattering. So there, I don't have the answer yet.
Okay, let us thank again Anina Salomon for a very interesting talk. And welcome our next speaker, Fabrizio from University of Po.
Exactly.
Please go ahead.
So actually this presentation is divided in two. It's myself, I'm Fabrizio Crocolo from the University of Po, and Alberto Vailati from the University of Milan, and I leave the floor to Alberto first.
So I have to have Fabrizio because alone he's not able. The project is a project that started in 2015 and involves several of the persons on this audience. Actually started several years ago with the Grazflex project, and this is a sort of continuation of the Grazflex project. It also involves an industrial partner, Nanotemper Technologies, and some Chinese partners within an agreement between ESA and the Chinese Space Agency. What is the project about? We want to investigate liquids, complex fluids, under non-equilibrium conditions in microgravity. This means that we take a fluid, a colloidal suspension, a polymer solution, or whatever. We put it inside a thermal gradient cell. We apply a controlled thermal difference to the sample so that we are able to induce a thermal gradient. And then by means of shadowgraphy, we shine a beam of light through the sample, and we look at the perturbation inside the sample in projection, just shadowgraphy. We are able to obtain a mapping of the fluctuations that occur inside this fluid. We have 4 parallel shadowgraph instruments like this in the setup, and each shadowgraph is equipped with a 2-color source, so that in the case of multi-component mixtures, we are able to decouple the contribution arising from the several components of the mixture. So I made the story very short. This will conclude the presentation, but to make a very short story very long, now I would like to give you some understanding of the basic principle behind this and why this is important. So let's go back to what we are doing about the outreach part. There is a consistent part of this project dedicated to the outreach. We already published a couple of papers aimed at students and stakeholders. to grab a full understanding of why investigating this kind of process is interesting, and also a basic understanding of the physics behind this. Here you see that in this slide we have put a cork inside a fluid. The cork is floating at mid-height inside the fluid. Why? Why is this possible? Because we weighted the cork by putting inside a steel ball, and the cork sinked inside the fluid. But why didn't it go to the bottom of the container? Because if the cork is denser than the water here, it should go to the bottom or float if it's not denser. So in the case, we have added some coarse kitchen salt to the bottom of the container. This coarse kitchen salt generated a density gradient. So the cork ended up sinking up to a layer which has exactly the same density. So this is hydrostatics, boring. But what happens if I apply a perturbation to this cork? If I apply an external perturbation, the cork is displaced from its initial position, and then it wants to go back to the layer with exactly the same position. These are called Brunt-Vasala oscillations. Brunt-Vasala are two meteorologists. So we'll see in a moment why this is important in general. Of course, beyond this oscillation, the oscillation gives rise to the production of a wave inside the fluid, an internal gravity wave, this is called. And this internal gravity wave is a transfer wave inside a fluid. So this is something very odd, because when you study physics, you learn that transverse waves are not allowed inside the fluid. So why this is interesting? This was well known since the times of Galileo. Galileo Galilei described exactly this kind of experiment. He told in this piece about the colloquium between Sagredo and Simplicio, you take a ball of wax, you put some salted water in the container, you put some pure water on the top, you put inside a ball of wax, and if you displace the ball of wax, it gets back to the original position. Why should it be interesting to investigate this kind of process, since this was already very clear in this old time? Because this kind of process is absolutely scale invariant. When you write down the equation of hydrodynamics in dimensionless form, this kind of process applies to the atmosphere, to the ocean. And of course, in this case, you should substitute the cork with a portion of fluid which undergoes an oscillation. And in the atmosphere and in the ocean, you see oscillations in the air or water occurring at the Brunt-Vasala frequency and giving rise to the propagation of waves inside these fluids. Now, what can we add interesting about this? What we can do is that we can perform experiments in a cell. As we have shown, this process is strongly influenced by gravity, which determines the oscillations and the propagation of the waves. So it becomes very interesting to investigate this kind of process under various gravity conditions, which can be met during space missions, and especially in microgravity when you don't have gravity anymore. So this is what happens on Earth at the mesoscopic scale. You take some fluid, this is a syrup, you put it in contact with water, and gradually the fluid diffuses into water. But if you look in the vertical direction through this, you don't see a homogeneous process. Why is that? Because here you see a patched thing like this. By looking from above, this is 1 millimeter in real space. Why do you see this fluctuation, these patches? Because this is a very nice cartoon drawn by Luca Cipelletti back in the 90s in a comment article done with David Waits on our paper in Nature at the time. Of course, if you have a large volume undergoing a fluctuation of a large volume of fluid can be driven by kT. You have velocity fluctuation inside the fluid. Velocity fluctuations are long-ranged. If you have a gradient in temperature or concentration inside the fluid, you displace this portion of fluid in a portion of fluid with a different concentration or temperature. So you have created a large fluctuation. This fluctuation is pushed back by the mechanism that we saw before on the cork. But what happens if you remove gravity or instead that the volume of fluid is very small? It could be that when you diffuse here, then when you move here, then diffusion is a faster mechanism in relaxing these fluctuations. And this is the kind of process that we can investigate under microgravity. We can completely read of these Brunt-Vasal oscillations and investigate the process in microgravity. But of course, the influence of gravity under various gravity conditions is very important also to investigate. So I leave the floor to Fabrizio for the technical part, the more technical part about this.
So thank you, Alberto, for this very nice part. So as we also see here, so there is different behavior of these fluctuations depending on their size. And if you analyze them by light scattering techniques, you can actually investigate the amplitude of this fluctuation as a function of the wave vector, which is the inverse of the size of the fluctuation. So for very large fluctuations, theory predicted, 30 years ago, that you have a Q to the -4 behavior, so larger fluctuations are much more strong, but at a given size, you have a cutoff given by gravity. And this was measured by Vailati and Giglio in the 90s and was the basis of the Nature paper. And then we developed also shadowgraphy to make measurements of the dynamics of the fluctuations. And you can retrieve from images, like the one you saw before, what is called the structure function, which is related to the correlation function of this fluctuation. And you can get information about the time decay of these fluctuations, as you can see here, again, as a function of the wave vector. And so you can see that for large wave vectors, so small fluctuation decay by diffusion, and for small wave vectors, they decay because of gravity. So from this kind of analysis started the GradFlex project. And in the GradFlex project, by means of shadowgraphy, it was measured the statics of this fluctuation. And so you see that these fluctuations are much more intense in space than on ground because there is not this limiting effect of gravity. But again, at some small wave vector, there is another limiting effect, which is the vertical confinement of fluctuations. On the other side, the dynamics is poorly diffusive in microgravity, as was demonstrated by the GradFlex project. So with this kind of measurements, so by shadowgraphy, we could investigate on Earth also the effect of the confinement. And you can see that varying the Rayleigh number of these experiments, you can obtain precise information of this limiting effect on the dynamics in this case. And we could do experiments on very thin layers showing that on ground you can obtain results. So these red points are from GradFlex, and the black points are from an experiment with very thin layer of fluid. So in a very thin layer of fluid, actually, the dynamics of the fluid is like in microgravity. And more interestingly, we could investigate mixtures where the confinement effects are not relevant, but the fluctuations couple at a given size, and again, they generate propagating modes within the fluid, which give rise again to Brunt-Vasala oscillation of these fluctuations. So you can observe this phenomenon also at the, let's say, mesoscopic scale on Earth. So This give rise to the giant fluctuation project, as Alberto already said before, where we have two fundamental objectives. One is related to the investigation of the fluctuations in several different conditions. For example, the fluctuations under confinement, under strong confinement, and the presence of the non-equilibrium Casimir effect, and a lot of different experiments involving complex liquids like containing polymers, colloids, and so on. And of course, this project has also very interesting applicative objectives related to the development of new investigating techniques like the two-color shadowgraphy that we could develop in different laboratories, and also the investigation of transport properties of liquids in different conditions. So this was also related to our collaboration with the Nanotemper company, and was supported by a MAP project from ESA, which is called TECNES. Alberto, I leave you again. Say some word about this.
Yes. So this project involves about 20 experiments that we will perform on the International Space Station starting for 2026. There is no time to discuss them all. I want just to discuss a single one of them. In this case, we have, when you generate this diffusion process by bringing two miscible fluids into contact or by generating a thermal gradient, we give rise to long-range concentration or temperature fluctuations. The question is, what happens when you confine these fluctuations? The answer has already been provided in the case of near-critical fluids. If you take a near-critical fluid, you go close to the critical point, you have a divergence of the correlation length. And then if you put a couple of colloidal particles inside the fluid, the fluctuations in the gap between the particles will be different from the fluctuations around, because here you are confining the fluctuations, and this results in an effective force applied to the particles, which changes their interparticle potential. And based on the seminal work by José Ortiz de Zarate, who was part of this project and unfortunately passed away a few years ago, and of Jan Sengers, who is still alive and kicking. I heard from him a couple of weeks ago, and he's still working on this. He's 93 at the moment. We plan to try to do the same in this liquid where we have non-equilibrium long-range fluctuation. The idea is to put a couple of colloidal particles inside this and see whether also in this case, without going close to the critical point, we are able to obtain a similar condition. And of course, a significant part of this has also been done thanks to the work by Sébastien, Vincent Bonnieux, and Marco Braibanti within the framework of the ESA white paper. So the idea was to start from the concept that we provided before and to widen the range of open problems and to highlight why investigating this kind of thing is important, not only for microgravity, but in general for space exploration. So this ended up in a publication on MPJ microgravity, where we addressed that investigating complex fluid like this under non-equilibrium conditions, I finished, is very important because the processing and the stability of complex fluid during space mission is of pivotal importance for the processing of food, fuels, materials. If you want to 3D print a material, you have to process a melted material. And this effort has been brought forward through the discussion which started thanks to this similar work. And last year we published an additional paper together with Valentina Shevtsova, where we address how also not only problems related to thermal diffusion, but also problems related to cross diffusion and diffusion phoresis would be very important to investigate. Thank you.
Okay, I take just the microphone to say thank you to all the people that collaborate in the 20 and more years on these projects. And you can see a painting by Marcio Giglio of Olivier Minster, who was, I mean, the two were at the basis of this kind of project. Thank you to all of you for listening.
Okay, we have time for literally one question. Because it's for people online.
Online.
No.
Thank you, Paolo Annibale, University of St Andrews, Scotland. I just have a technical question on this shoutography. So what is your spatial resolution in these imaging experiments?
So just to have an idea, we observe the size of the image that we observe is in the range of 1 centimeter, between 1 and 2, and the spatial resolution is 2K pixels. So you divide. I mean, you are in the 100 microns, so it's large. But we observe the fluctuation of the density, so we don't see molecules, we just see volumes of fluid.
Okay, let us thank Fabrizio and Alberto once again. Thank you. And James. So our next speaker is James Lutzka from Université Libre de Bruxelles.
Okay, so I'm Jim Lutzko, and this is my colleague Stefano Buzzacaro, and we're going to describe the COLIS experiment, the COLIS instrument. Stefano is going to begin and discuss the technical aspects of the instrument, and then we'll continue jointly with some science that we're doing.
So good morning, everybody. And why COLIS? The idea of COLIS is to investigate the origin information and dynamics of soft solids, so crystallization, but also the properties, the dynamics of the glass transition. So if you want some arrested system in which the driving force is a repulsive force, but also we want to study attractive glass and gels, so in colloidal system in which we have a short-range attraction. And we want to study also protein nucleation and crystallization. And all these phenomena, we want to study the spontaneous dynamics, typically, but also the driving dynamics. And we will see in this instrument that we introduce a not standard way to driven the system. Why we need for microgravity? I don't know what's happened. Okay. Here you should be supposed to have a movie. Or two movie, and the slide is stuck. It's cracked. Okay, good. Okay, I can describe the ideas why we want to study this system on space. Of course, because with gravity, if you have a soft solid, this gravity can deform the material. Here, you're supposed to have two videos. One in which we have a gel that collapses under gravity, but the gel doesn't destroy. You simply see that it's compressed. We skip, I think, we skip the second, or another possible mechanism is the formation of aggregate, and of course, in this case, can lead to the rupture of the gel, and you see the gravity, they settle. But there is another more reason for that is that in many of the systems that we want to study, the interaction can be controlled by temperature. So we can tune the temperature and tune the interaction between the particle. But of course, if you do that on Earth and you apply a temperature jump or a variation of temperature, it's really, really difficult to avoid the presence of convective motion of the fluid. In this case, can influence the formation of the aggregate for protein or the formation of the gel. And the last idea is that many of the systems that we want to study is material that lives in water. So the solvent is water, and if you want to study this material with optical method, you have to index matching the optical properties of the particle and the solvent. And one of the drawbacks, if you think about colloidal particle, essentially the only way to do is to use fluorinated particle, but they are really dense, so it's practically impossible on Earth to have a system in which there is transparent in water and in which the density of the particle is equal to the density of the solvent. So this is the reason to move to the space station, and this is simply the idea of what is COLIS. COLIS is essentially an advanced light scattering setup in which we have a green laser and 3 DLS standard dynamic light scattering line at 3 angles, 90-degree forward direction and back scattering. And then this is coupled with the 3 more innovative photocorrelation imaging setup in which the scattered field is collected by 3 cameras at the same angle of the DLS setup. Then we have a small angle light scattering setup, the standard one. And one of the novelty of the system, we have also a near infrared laser. This is partially absorbed by collinear with the probe laser, the green laser, that is partially absorbed by water, and so we can locally hit the sample. And the other thing is, of course, we have a cell. The design the scheme is simple, but at the end, probably you know the realization is much more complicated, crowded. And this is a typical example of the cell in which you can see the all the diagnostic of the sample. And we call cell modulus because it's a huge object. The idea is it should be a modular system, so you can insert the cell, and then if you want to change the experiment, you can remove the cell and add another cell modus. And the idea is that in principle, you can create different cell modus if you need experiment with the different properties. This is 2 examples. This is for the experiment for glass and gel. The idea is to have a cell in which you can precisely control the temperature. For studying the gel and the glass, the typical duration of the experiment are weeks. So we are to be sure that the sample is at a fixed temperature for 1 week or more, because we are using system that the properties change with the temperature, so fluctuation in the temperature could be a problem. And of course, inside the cell, there is also a steering mechanism that is able to steer a fluid that has a viscosity that is at least order of magnitude larger than water. And just to give you an idea, the cell, the real optical cell, is this tiny point inside the cell modulus. This is, on the contrary, another cell modulus D that is for the protein experiment. The idea is more or less the same. The difference is that here we have less optical access because you need only turbidity measurement and light scattering at 90 degrees. So from this point of view, the cell is much easy to deal. But for protein sample, we need to work with a limited amount of samples, so the cell volume is much more smaller. And another thing that is very critical for protein is that you have to be able to create very fast temperature ramp, and to do that, instead of a single big Peltier element, we added 3 small Peltier around the optical cell in order to have a better control of the thermal properties of the cell. And here, this is essentially the sketch of all the system, and what we can do, okay, we can tune, of course, the intensity of the laser, but the laser, there is a shutter, and we can also control the timing of the laser. Here is the DLS line, is a classical DLS line with the photocorrelator. And what I think is important, we have in front of the sensor, the photodiode, the polarizer, so we can perform a polarized and depolarized light scattering. This could be important for many different situations. And this is, on the contrary, the PCI scattering angle, so we collect the images with the camera, the same angle. Of course, there is a lot of, for space constraint, there is a lot of mirroring in order to bend the light path. And this is the typical image that you obtain at the 3 different camera in the photocorrelation imaging configuration. So see there is a speckled pattern, and what you can do is, maybe you are more familiar with classical dynamic light scattering, you correlate the intensity fluctuation averaging in time. The advantage of the photocorrelation images is that instead of averaging in time, you can average in the pixel number, so you can also follow the dynamics of systems that are aging. And another advantage of the photocorrelation imaging is an imaging technique, so you can see the spatial information, and so if you have spatial heterogeneity, in principle you can visualize them. Okay, I think that the video that I have crashed the computer, because here there is another video that probably doesn't work. Okay, this is the video in which is the only part in which I show data with the gel sample, because of course we cannot make experiment on the gel sample because on Earth they collapse, so they disappear. So the only thing that we can do on Earth is check if you are able to remix the sample, if the generation temperature is the same, and in the images you should see the formation of clusters. So we exploited the imaging capability of the photocorrelation imaging to see the presence of bright spot that demonstrate the formation of cluster or aggregate. Here I show you very simple experiment that the idea is to validate the instrument. So here is the DLS light scattering, the 90 degree at 3 different realizations that work perfectly as you expect as a single exponential. This is for a very simple diluted colloidal sample that we know the size and everything. One of the problems that we recognized was in the backscattering, that you see that there is 2 time and this, 2 characteristic time. This is essentially due to the fact that there is a back reflection inside the detector, but once you correct for this reflection, you will obtain the diffusive behavior that you expect. And what is nice is that this data with the conventional DLS in the lab, and this is the Collis DLS, and also we can measure the viscosity of, the diffusion properties also using photocorrelation imaging. They are absolutely consistent with the DLS. The second data was related to the depolarized light scattering. So again here, VH stays for the fact that you illuminate the sample with a vertical polarization, you collect the light in the horizontal polarization, and we will see that again there is a problem that is come in the back reflection, so is confirmed, but is much less visible in the horizontal direction, because if you have a reflection, you are collecting a polarization that is perpendicular to the incident one, you essentially remove this effect. What is clear is a little bit technical, but essentially this data cannot be easily fitted with a simple exponential, but you have to add another terms because the polarization, the removal is not perfect, so you have also a small amount of vertical polarization that enter into the detector. This is essentially due to probably to the stress by refrigerancy of the cell that is difficult to eliminate in these cases. But at the end, when you correct for this effect, you can recover the behavior that you expect for polarized dynamic light scattering and the polarized light scattering. And the last image is, the last part is for the SAS. This is the typical image for the SAS with the beam stopper. And here we have the data that is confirmed that the things work quite well. There is a problem at a low Q angle. This is essentially due to stray light and a perfect removal of the beam stopper, but all is predicted with what you expect with the theory. So also the SAS works. And now it's time, this is the calibration of the system, a bit of science, so it's time for Jim to discuss about protein.
Okay, so one of the science experiments which will be in the first mission using the Collis instrument has to do with protein crystallization. I just mentioned briefly, we are interested in protein crystallization for a lot of reasons. There are technological reasons having to do with the production of pharmaceuticals. Also, because proteins, because they're large molecules, they're easy to see and move slowly. They've been a paradigmic system for understanding non-classical nucleation mechanisms. So this has more to do with basic science. And there are a lot of ongoing mysteries about protein crystallization. We always, well, not always, but we often see the formation of clusters that precede the nucleation, and we don't really understand the nature of these clusters or even why they exist. And so one of the interests is in trying to understand these. Also, there have been experiments in space on protein crystallization going back to the 1980s with mixed results, some showing an effect due to microgravity and some showing no effect. So one of the reasons to do it in microgravity is, again, to try to settle this question of whether or not it's important, and if so, what is the mechanism? We think that microgravity, when it's important, may be due to its role not directly on nucleation, of course, but on these mesoscopic clusters that precede nucleation. These are some results from ground tests that were done in 2023 using the engineering model. What you see on the left is a DLS signal. So this has to do with, we're planning to do two experiments. One is called the precursor protocol, which is to understand how the population of precursors in the solution changes as a function of temperature under microgravity. So we heat the protein solution to 40 degrees to melt all of the crystals, and then we let it equilibrate, and then we lower the temperature in steps of 5 degrees, and at each temperature 5-degree increment, we let the system equilibrate and measure the properties of the precursors. The left is a DLS signal. You can see the raw data as well as a fit using the content algorithm. You see the two shoulders, which the first shoulder has to do with the detection of the monomers, the protein monomers, and the second one has to do with these precursor clusters, which are in solution. When we process the data, we find that we get two peaks in the size distribution. One is at 2.4 nanometers, which is typical of the size of a protein molecule. And the other is at 125 nanometers, which is typical of the sizes reported in the literature for these clusters. A second experiment we're going to do is to go directly from 40 degrees to a low temperature, around 10 degrees, to induce crystallization, and to measure the induction time. To do this, it's very important to have a very precise and reproducible temperature control because we're planning to cycle the experiment. So on the left, you can see these are actually 5 different cycles of raising the temperature to 40 and then lowering it to a set point of 10. What this figure demonstrates is that the instrument gives us a very reproducible temperature profile. This is decreasing the temperature as fast as possible while trying to minimize the undershoot relative to the set point. On the right, you see the turbidity, which is measured. We have a laser which we measure the power of a laser which goes through the sample and compare it to a reference which does not. And when crystals form, the turbidity goes up, so this is a signal of crystallization. And again, you can see very reproducible results over 5 or 6 runs. Okay.
Okay, I come back for a very quick explanation what we plan to do with the glass. So instead of using classical R-sphere material, we use PNIPAM particle. The idea is that if you change the temperature, you can change the volume, the effective volume occupied by the particle. And so with a single sample on space, changing the temperature, you can probe different glasses. And here, one thing that we do is a nice new thing. You know that if the particle changes size, they change also the intensity. So if you measure the intensity variation with the temperature with the 90-degree camera, you can essentially, at variance with the temperature, you can have a smart way to measure the temperature inside the cell. So this is the experimental result in which we shine the near-infrared laser inside the cell, and we saw that the temperature map, so we are able to measure the temperature inside the cell. And what we show is that, of course, as we expected, the temperature is not uniform, but this is what we want, because using the laser, first of all, we can have a temperature jump that is faster than the classical variation of the temperature of the cell that is still possible. And another thing, we have a gradient in temperature in order to see if there are some effect on the presence of the temperature gradient inside our material. Here is two measurements simply at two different temperatures, at 28 degree and 25 degree, in which case we have an equilibrium liquid as expected. What is nice is that 25 degree, on the contrary, we reach the glassy state. I don't have time to enter into detail of the properties, but people here that are involved in glass probably should recognize the effect. In particular, you can see that the keys for increase, there's a signal that with time we have edging, the formation of heterogeneous dynamics. And the last part, of course, we can also probe the glass sample with the infrared laser, with a pulsed infrared laser. And what is interesting to show is that the red and the green curve are two glasses at the 28 or 27.5 temperature without the laser. We say that the evolution of the correlation function is low, it's an arrested system, but if you start to cycling the temperature inside the gel, you promote plastic rearrangement that speed up the dynamics of your material. So essentially, the conclusion I can skip is essentially the resume of what we have presented to you. Let me to say that we plan to have the first result on space. Everything works well at the end of the next year. At least for the protein and the glass sample, because the gel sample will fly later. This is the team that is coordinated by Luca Cipolletti of the University of Montpellier and Professor Roberto Piazza from the Polytechnic of Milano, Jim, that you know, and Dominique Kenken, that's the collaborator of Jim about the protein. Of course, Redwire, there is the company that built the instrument. And this is a paper that is in the second round of review about the collies. Thank you for your attention.
Okay, again, one question.
Well, who built the instrument? I missed that.
Sorry?
What company built the instrument?
Redwire was the old kinetic.
Redwire.
Redwire.
And which part of them?
I don't know. In
Okay,
the
so
sense, no, I know
maybe
the original
discussion.
company, the name was Kinetic from Belgium, but then it was acquired by Redwire.
Yeah.
So now I say the Redwire, but I think that the 95% of the building of the instrument was made by the Kinetic company.
Good, thank you.
And the optical part by Lambda X.
And maybe just the last one. So, do you see a fundamental reason why an experiment or a setup like yours could not be built larger, let's say one order of magnitude larger? So your sample cell is like 10 millimeters?
The size of the cell, the optical cell is less than 10 millimeters. Is
and
5
is there a
millimeters.
fundamental reason why it couldn't be larger? Like I'm thinking
No,
temperature
one of the
heterogeneity,
thing
for example?
is, one of the problems that we have when we design the system is that for photocorrelation imaging, you want to illuminate all the samples. So essentially, you want to spread the laser, but the same laser should be used for dynamic light scattering. In these cases, you need the opposite to concentrate the laser. So the size of this laser, the beam weight is around 2 millimeters. It is a compromise between the imaging capabilities. In my lab, for instance, I image gels with the size of 1 centimeter or 4 centimeters. But I don't need to do, at the same time, also DLS. On the contrary, if you imagine a classical DLS experiment, you focus the laser on a size that is tens of microns. So this is essentially the reason. And the second one is that if the cell is too big, it becomes also difficult to control the temperature.
Thank you very much.
You're
Okay,
welcome.
let us thank both speakers once again. It is indeed. And welcome Luigi Cristofolini from University of Parma. Please, Luigi, go ahead.
Thank you. I'm presenting results from a collaboration involving my group in Parma and the CNR ICMATE group of Libero Ligieri, Francesca Ravera in Genova, and the group in Thessaloniki led by Professor Karapantsios, and my good friend James Ferry, and in Virginia Commonwealth University in the US, and Sebastien, who is in the audience as well. So it's an experiment that we started to get some results 2 years ago, so it's not as mature as the experiments on foam, of which we heard a nice presentation early in the morning, still on the same kind of subject. The outline of my talk will be we talk about why emulsions, and then show some results and discuss future prospects in view of this particular workshop that is exploration science. So why emulsions? Emulsions are transversals to a number of technologies and products of everyday life and advanced technology, starting from food science and technology, not only mayonnaise, as we all know, but many of the foods and bread and things that we eat and ice cream are either emulsions or foamy emulsions or mixtures, polydispersed mixtures of different immiscible fluids. Not only, but pharma and for cosmetics, if you think of a controlled drug release, it all relies on formations of small droplets of immiscible fluids and controlled permeability. So in control release and stability, all this relies on emulsion science and technology. Cleaning itself, when you wash your hands or when you wash clothes, well, there's a first mechanical cleaning process for the larger amount, but then if you want the surface to be really clean, you have to emulsify the remaining soil by emulsification with some suitable surface active agent and remove the soil contamination to have a clean surface. So it's a problem of emulsification again. Lubrication, as I learned, I didn't know this before I started this adventure. I learned from my friend James Ferry, when you have the engine, combustion engine, you have production of water. It's obvious, I didn't think of this, but you produce water, of course, and you need to remove this water from the cylinders, and this water is removed by emulsification in the oil, and so it's a problem of emulsification, but water needs to be removed, so the emulsification of water in oil in the filter. So it's a problem of continuous emulsification and demulsification, which has to be efficient as the number of cycles that the piston is doing per second is quite high. Not only, but we all know paints and coatings are based on suspension, either colloidal or emulsions. Oil industry, oil extraction, we all know oil extraction is based on emulsification with high pressure deep in the rocks, and then extraction, and then demulsification for the separation of the oil fraction from the water. So again, formation and emulsification is a pivotal point in the process of oil industry. So we understand that stability is important. Basically, all emulsions are metastable, except the microemulsions, but I won't talk about them. So let's say all emulsions are metastable. The fluids are immiscible, they tend to separate. They are, in practical terms, they're kinetically stabilized either by surface active agents like nanoparticles, surfactant molecules, proteins, or a combination of them, or by tailoring the mechanical properties of the fluids, by adding something that changes or modulates the mechanical properties of the fluids. And as I was anticipating, in some applications, emulsion breakup is desired, as the case of oil extraction and lubrication. Most often, we want the emulsion to be stable as long as possible because of shelf life of the product, for instance. In all cases, understanding and controlling stability is crucial, and the state of the art of the comprehension of stability is quite empirical. It's based on empirical concepts like, I won't go into the details, but something that is really a rule of thumb, HLB is hydrophobic to leiophobic balance. That is something, an index that people use, but it's not really well understood what is behind that. Stability by surfactant is obtained by different kinds of surfactant, can be non-ionic, anionic, cationic. We know cationic surfactants are quite dangerous to the environment, harming the environment. So there's a research in substituting ionic, in particular, cationic surfactant by non-ionic and obtaining same results with less impact on the environment. Fluid thickeners like xanthan, for instance, are commonly used in food, and they impart non-trivial properties like viscoelasticity, which is a frequency dependence of the mechanical properties, which is the case, for instance, when it's something that is elastic on a short time scale, but then it starts to flow on the long time scale. And so this is the framework. And why doing this in microgravity? Why microgravity is relevant to this kind of process? And this is because different destabilization mechanisms can occur concurrently in emulsions. First of all, let's think of droplets that move around, and they could aggregate reversibly by keeping their identity. So this process is called aggregation. The aggregation can become coalescence if two drops come together and merge into a single bigger drop. Oswald ripening is the process that was described maybe with a different name, but it's the driving mechanism that was described by Anina for foams. So it's surely very important in foams, maybe important in emulsions when miscibility of the fluids is not negligible, or in the high content, in the high surfactant content regime, where we have micelles that are exchanging matter between drops. So Oswald ripening may be also important. And all this is convoluted normally with creaming or sedimentation based on the difference in density. And all this leads finally to phase separation. Going to microgravity, limiting buoyancy allows to observe intrinsic droplet dynamics, so observe these three phenomena, and to isolate the effect of each of them. So that's the motivation for microgravity research on emulsions. So this was the kind of introductory part. Now I apologize, I go a bit more into the technical part, but not too much. The main parameters that describe the emulsion, in my view, is the drop size distribution, not only the mean value, but also the moments, so how broad it is, how symmetric or asymmetric is the distribution. Average drop distance. What we do observe actually is the mean displacement or the mean square displacement of drops, which in different dynamical regimes follows different law with time. If you have diffusion, Brownian diffusion, we all know the mean square displacement grows linearly with time. If you have constant velocity, which in the jargon of spectroscopy is called ballistic motion, you have an increase with the square of the time, so it's constant velocity. Of course, you need a driving force for this because you're in a dissipative environment, so to keep a velocity, you need a force. So you have also to question if you observe this, why you observe it. Confinement effect, on the contrary, limit this growth of the mean square displacement. And we use diffusing wave spectroscopy to follow the emulsion as a function of age. Very briefly, what is diffusing wave spectroscopy? It's a particular version. It's similar to the DLS that was mentioned just by Stefano in the previous presentation, but performed in an opaque environment. So you have many scattering events. Basically, you don't know the exchange momentum. You have a mixture of soup with many exchange momentum. You can make models, and this particular moment is more important, but it is not always easy to do it. Just imagine, if the sample was all static, the illumination is static, interference freezes will be static. If something is moving, it is because, if you observe some motion here, it is because some motion is happening in your sample. And by calculating either the time average or the ensemble average, as the PCI technique was mentioned just before, we don't use a camera, it's a line camera, small differences, but the idea is the same. We can have a measurement of this velocity of the change of the dynamics by calculating the correlation function, this kind of technical part. And the classical interpretation scheme for this is that you collect DLS in DWS in two geometries, typically in backscattering and transmission, and by comparing the two, you get the mean transport length in the sample and the information on the dynamics and the scattering centers in the sample. When I approached this technique for doing the experiments in space, I soon realized that this classic scheme applies only in the infinite slab geometry nicely. And if you have to be accurate, you have to take into account also the finite size effects that limit the distribution of path length that in principle would be accessible. For this reason, we developed a new philosophy of analysis of DWS based on optical Monte Carlo simulations of light diffusion. And this is not the same as solving the diffusion equation in the system because scattering is not a true diffusion system. So it is, I believe this is better than solving numerically, because you could also solve numerically the diffusion equation with similar results in transmission, but with some important differences in backscattering. The code is available online on GitHub and MathWorks if you are interested, and we can discuss details. But what I want to show that by this approach, on ground, we are doing experiments with a model that is called the elegant breadboard, which is a copy of the instrument on orbit. So these are data taken on ground on an emulsion very similar to the one that are flying on the ISS. Of course, on ground, as soon as you make an emulsion, you observe creaming. You don't need a very sophisticated technique. You just see by eye that drops are going up. But if you want to quantify them, and you want not to be influenced by the walls, because what you observe by the walls is maybe influenced by the presence of the walls. The flow, for instance, will be surely influenced by the walls. So by DWS, we explored both the bulk of the volume, and we model the data with I won't go into the details right now, but we can directly model the data with the diffusion constant and the velocity. And to make a long story short, the diffusion parameter is characterized by these squares here, and the velocity is represented by these round points here. So on a time scale of a few minutes, we observe the ballistic motion or creaming. We are in gravity now in Parma, so G is 9.81 in Parma, I don't know here. We have velocity, the time is short of velocity for some time, then velocity ends because of the creaming. Of course, what you observe really depends on the position in the cell. If you're sitting in the middle where you still have some drops, not too many, some drops still diffusing, then you can observe the average size or the diffusion time, which is not affected by this creaming. So creaming is ending and you still observe something. Of course, if you do the experiment at different height, you would observe the disappearance of the signal or packing and confined motion. So it's heterogeneous. So with this framework, having validated this approach, we go to the ISS. We flew, in the 2022 campaign, we flew 15 compositions. So not as the 68 foams, but still a number, made of MCTs, coconut oils, of edible oil, you could eat it, in water with different ratios, and with ultra-pure surfactant provided by Nickel, who is a partner in this collaboration, Nickel Japan. And they are stabilized by the non-ionic surfactant of the family of CEJ, C12EO21, which partitions to water mainly. So an observation from the overview camera, you can, if you remember the pictures that Anina was showing early in the morning, it's the same camera, they call it overview camera, so it's 11 by 14 millimeters, 11 by 11 by 14 millimeters, the sample cell, the important part of the sample cell, all the rest is taken by the piston. The emulsion is really just generated with the piston the same way as the foam was made. Maybe small differences we agitate at 19 Hertz, a bit faster. We can discuss this later. What is important to notice is that the emulsion that we produce is very polydispersed. This is something that probably is more important in emulsion than in foams, but it has to be taken into account. And when you have such a large polydispersity, a single technique often is not enough to capture the diversity of size from the smallest ones that are not observable by microscopy to the big ones that escape from scattering experiments. And our friends in Thessaloniki made a full characterization of the drop size with a technique. I mean, they freeze, they make the emulsion with the very same geometry and a similar cell, and they freeze the emulsion as it is made, with diluting it in a high surfactant content, and they observe by microscopy. I have some doubts, because when you observe by microscopy and you count the objects, when you have very many of small ones, but they manage the complexity, and they come out with a bi-disperse distribution in which most of the oil by volume is in the big humps here, which will not contribute mainly to the DWS, but you have a consistent number of small drops, which on the contrary are the ones that contribute to the scattering experiment, mostly contribute to the scattering experiment. So having this in mind, we go to the data. I just jump to the results. Here I'm showing data from, this is the 20% oil with increasing surfactant content, and this is the radius that we observe as a function of time, is growing with time. Radius is growing with time, with the different lows depending on the surfactant content, and it reaches up to some saturation value. At the same time, the transport length that we also extract from the same experiments, in some case grows with a power law. If we keep in mind the picture of big and small drops, this can be rationalized, thinking that at early times, the driving mechanism for evolution is the coalescence between small drops. So the two small drops merge, thank you, and they make a drop that is larger. So the radius of the small drops is growing by this mechanism. If, on the contrary, I have merge of a big drop and a small drop, the result will be that I have less small drops, because the radius of the big one won't significantly increase, but the number density of the small drops will decrease. And if I have merge of two large drops, that's an earthquake. It will not appear directly in the DWS signal, but it will appear as an earthquake, as a motion because of hydrodynamic relations, as a motion of the small drops that I might probe. So having this picture in mind, the evolution of the radius could be identified with the merge of two small drops, and the evolution of a star at long times as a merge of small drops to the big ones. This could be driven, for instance, by the number density of small drops, which is decreasing, so the process is becoming less important. The time scale here is a logarithmic scale. Just to notice, it is 5 days in the end. So we have repeated 2 hours for many times, and we have a couple of repetitions of 5 days to give the idea of the statistics that we have for this data. So this is what I was saying. The picture of emulsion evolving by this coalescence process is corroborated by the analysis, a more detailed analysis that is ongoing. By the way, this part was published, and this analysis is ongoing, by multiple scattering or the line camera analysis of DWS, by multispectral analysis. We can identify more precisely the kind of mean square displacement that we have as a function of time. And we observe that while normally the motion is Brownian motion, and this is represented as mean square displacement that is growing linearly with time, this dashed line is what you expect for diffusion. From time to time, we observe an acceleration of the dynamics, so the correlation function decays faster, and a change in the shape of the correlation function, which results, if you translate it into a mean square displacement, in an increased slope, which we can model, again, remember what was showing in gravity, we have creaming immediately after emulsification, and then creaming ends because it's ended. In microgravity, far from emulsification, so we are here at 26 minutes after emulsification, so half an hour, so no eddies are left. We observe from time to time that there is a dynamic transition, the transition between different dynamical regimes from Brownian diffusion stationary regime to ballistic motion, which is represented by this velocity that is appearing for a few seconds and then disappearing. And this ballistic motion is intermittent. So it starts and ends and starts and ends. We can also count the number of events as a function of time. We're in the process of working on this. This transient acceleration that happens over a stationary Brownian diffusion is something new. To the best of my knowledge, it has not been observed. It's different from the transients that you observe in foams. This is well known. Foams are arrested, and then from time to time, some rearrangement occurs, and this is how you characterize them. It's different from avalanches occurring in an arrested system. Ours is not an arrested system. It's a system in equilibrium, with dynamic at equilibrium, which from time to time gets out of equilibrium for internal reasons. What is this internal reason? In my view, this has to do with coalescence. And this can be related to coalescence by two different mechanisms, either by obvious hydrodynamics correlations or because of a more subtle mechanism related to surfactant. It's Marangoni-like forces. And these cartoons here shows, if you have two drops the same size merging, you get a single drop that is cubic root of 2 larger. There's a reduction of interfacial area of the order of 20%. This reduction of interfacial area may result in surfactant release. The surfactant release generates a gradient of concentration, which results in a force, Marangoni-like force, on the surrounding droplets. So this is also possible. We're in the process of understanding which of the two, maybe both mechanisms are important. So, but at least by comparing the velocity to the growth of radius, they have the same time. They have the same time dependence. So we are quite happy with the result. We think we understand something. We have to do more. Want to just to mention other activities in collaboration. I mean, activities led by the Thessaloniki group. They have a fast camera and look at the dynamics of drops. They're coming now to Parma and do the same experiments with the ABB and want to see the drop dynamics in the sample cell directly. And the EBB is also used by the other experiments that are going to fly next year, the oily foam by NLOR, and the lunar dust coordinated by Carlo Saverio, and the graphene experiment coordinated by Antoni. And with this, I thank you for your attention.
Okay, one very quick question, please go ahead.
Thank you. Fabio Giavazzi, University of Milan. Just a curiosity, in the video you showed, there seems to be a lot of collective motions. Like there was a large-scale motion of the bubble. And
you're right. That was taken immediately after emulsification.
I see. So it was still an effect of the emulsification process.
Yes, we are in the process of understanding how much time we have to wait before the eddies stop. If you look at we have a calibration sample that is a dispersion of polystyrene in density match normal water and deuterated water so that they have the same density. And it seems that we have kind of 10 seconds in that case of eddies. With emulsion, they last longer, probably because of merge of drops that are happening very fast. And that's motivating the investigation with the fast camera, because I think there's much more that is related to emulsion than what you would normally have only for hydrodynamic reasons.
Thank you.
Okay, so we are going to keep all the other questions you have for the discussion we have on, during the next session. And thank the speaker once again. Thank you, Luigi. And the following presentation will be our last presentation in Duetto of the day. So please welcome Matthias Sperl and Jan Gabriel from University of Cologne and the DLR. Please go ahead.
Thank you, Olfa. Let me also thank the organizers, Marco and Sebastian. I know we've been through the soft matter dynamics instrument for a large part of our careers. I also have met probably all the speakers previous to that in our arguably largest soft matter MAP program, a program which should find some replacement for supporting the science in microgravity later. Okay. Next slide, please. Oh, that's me. So I tried to argue a little different from its usefulness for grains. So grains are arguably the hardest physics you can do, and the New York Times must know. I think it's clear to most people here that sedimentation of grains is something you experience in everyday life. And I will show on the next slide some details of that. So we try to exploit microgravity for understanding better granular materials. And I sort things into different densities. And Jan will then specifically look at the laser light scattering in the soft matter dynamics instrument. So if you have very dilute grains, it's clear they sediment on Earth. They don't do that in microgravity. We have a nice magnetically shaken granular system where we were able to investigate the deviation from the Maxwell-Boltzmann distribution for the first time, which has entered textbooks in the meanwhile. There are granular fluids where I leave the floor to Jan to explain the difficulties. So even if you blow things like in a fluidized bed, it's still inhomogeneous, and you want to get rid of that anisotropy, and you can do that in a suitably performed space experiment. For yet denser systems, we have a nice instrument on sound transmission, which is ready for launch and will be up there in October next year. Here the physics is that if you go to lower and lower pressure, you lose sound. And it's an interesting question, how do you lose sound? Is that a critical behavior? What happens here if you go to lower and lower static pressure? And I'm proud to announce that we have the world record in the slowest sound speed in the glass bead packing. So you can almost walk by it. In terms of applications, we had the luck during the ESA mission of Matthias Maurer to have an equally named Mason experiment investigating the solidification of concrete with many, many nice experiments. A payload developed solely by the PIs directly. We had 64 samples and all of them worked out. Here is a PI astronaut experiment where we used ellipsoidal candy, I'm not allowed to say M&M, for looking at rotational dynamics of granular media. And with that, I would hand over to Alexander Gerst and Jan Gabriel for the light scattering experiment.
Thank you, Matthias. So yeah, we have heard about this experiment. So the soft meta-dynamics module, we use that. It's originally, as we learned, done for foams and emulsions, and I will now present how we use it for grains. So we are interested in the dynamics of grains and actually in the losing of the dynamics. So we look at the transition from it can move and it cannot move. And so we have basically a sample, which you can see from top here, and we have a sample cell, and this small area is basically where we can observe our sample with our light scattering technique, which I'll explain soon. And our system is a dense dissipative system, so these are polystyrene spheres, and we agitate it with soft pulsed agitations. So and therefore this system is basically quite non-ergodic, and this gives some trouble, but the problem of classification is inherent, like a non-ergodicity problem. So the basic setup looks like we need a sample cell where we can put in an agitation, and we use piezo crystals here, and we want to basically change the volume so that we have more or less space for our dynamics. The agitation is quite tricky, so what we choose is basically like this pulse agitation. And with one of the detection methods, like with the line camera in backscattering geometry, we can basically observe already the dynamics here, or the non-dynamics. So these are basically speckle. So it's an interference pattern from the coherent light, and this will fluctuate if there is dynamics. And as you see, over time, there's nothing moving, and then we do our pulse, then we go into a different state, basically like in one direction the piezos are expanding, and in the other direction they're contracting, and vice versa. And so you go basically from this speckle basically back to this speckle, and it changed a little. And so we can determine how much did the sample change, basically. Now I'm going to the very fast dynamic, which we do with fiber optics and avalanche photodiodes, and then hardware correlation. So we can go basically in the nanoseconds. We can see that the correlation, which we can calculate from the fluctuation we measure, is not decaying because nothing has happened. Then we have our contraction and expansion of our piezos. So our correlation function vanishes, and it returns to some certain degree back when we are in the back where we have been before. And since this is logarithmic, these oscillations are getting faster and faster and faster. And at some point, actually, it's oscillating faster than the time we are averaging over. And so we pick a way where we make this averaging by we force it to make an average so that we have a defined point where it changes, basically. So the agitation is quite complicated. So we have basically an acceleration pulse and then a deceleration pulse, which gives us some velocity profile. Actually, for the kicking, the acceleration is the important part. But we end up with this profile, and we can use this profile and put it and calculate basically the response to that. And then we need an assumption for what is actually the dynamics of the particles. So if we can fit that, we can actually extract the dynamics of the particles. So we start with something ballistic, then we have some power law behavior, and it might be diffusive in some cases, not on the ISS, but we will come there. So to have a reference system, I will present you first some easy results from a voice coil experiment. So we shake the whole container, and then we can actually, the agitation looks then a little bit different, but we have a well-defined acceleration and velocity profile, and not so complicated. The calculations are much easier. And the results are basically, if we have like 3.7 g acceleration for these particles, basically over time, we get a packing fraction of 45, and we can observe this simply by visually that it is compactifying. And if we go lower, then we see over time basically a compactification, and this is also reflected in the backscattering and in the transmission signal. So the backscattering signal comes mainly from the surface, while the transmission is going through the whole system, and therefore it's actually decaying faster because this has more scattering events, so you can decay the correlation function faster. And so you can observe basically that the mean square displacement is only in this regime. You can reach a ballistic, you can observe ballistic, diffusive behavior basically. Yeah, and that's actually due to the light is very small. Our particles are 140 micrometer, so they are only flying basically freely 10 nanometers, and then they are already stopped and interacting. A direct comparison looks like if we do this shaking experiment, we have actually a very heterogeneous system. So backscattering and transmission gives us totally different levels of how far can a particle fly. And now we look at our sample cell where we have the piezo's, and we have again very different correlation functions, but they look much similar than the ones before. So this agitation gives you a much more homogeneous agitation for the system, and we have still some differences which we see later a little bit better. So on the ISS we did actually, so since it's a non-ergodic system, we need to measure very long. So we was able to convince them to measure basically 10 hours for one packing fraction. So you go up the packing fractions, and then you go down the packing fractions. And after one of our runs was basically in the end 300 hours. And yeah, then we have a lot of data, but we are able basically to resolve partially this long time behavior. So we choose an agitation so that we are able to somehow decay the correlation function, and it takes really long. In the case of the ISS, we get basically the same power laws everywhere in the sample, so backscattering and transmission are similar, but there is a slight heterogeneity, and here, yeah, on ground we have still some difference between the wall and the actual sample in the core or the whole sample. On ground, which is not so surprising because before I showed you basically the shaking experiment where the wall and the center was basically totally different. So the direct comparison is that we observe different power laws in the transmission, where we don't know yet really how to think about that. And in the wall we see basically at the same packing fractions now on ground and on ISS. We see that the wall is again behaving different than the core volume. And now, since we have a camera, we can actually measure a non-ergodic system. So if we now approach like really dense systems, the dynamics should go down, and this should be a kind of glass transition or a marker for a glass transition, that the dynamics in our sample is going down. And this is what the correlation functions actually already suggest, that if you go lower and your dynamic is decreasing, and also your mean square displacement tells you, okay, the free space I can fly gets less and less and less. And it also shows that our fit is actually making sense because it results in the same free path velocity, basically, in the region where we can actually show that. So now let's observe the glass transition basically by plotting this mean square displacement length and comparing this to the diameter. And so we get basically at 45, so very loosely packed, it decreases, and then we get yeah, our glass transition basically quite rapidly. We can observe that over this 1% basically in change of density, and we repeat it a lot. It's a very since it's a non-ergodic system, you always prepare different states, and it's really hard to make sense of it because we tried several protocols basically. So 1 hour runs, 5 hour runs, 10 hour runs, working on one density and then densifying. But yeah, the overall signal is the same. And what I don't show here is basically that we see this. We cannot really observe this glass transition on ground. It appears in our ground measurements, which has to come in the paper soonish, hopefully. Yeah, that's this part. So, Matthias, do you have some outline?
Okay, so I have 5 more minutes, which is plenty. So I'm happy to give some outlook, and you have the laser here. So 2 things I want to advertise, also leading over to the facility definition. So for all mesoscopic systems with 100 micron feature size, but especially for grains, we are happy to ramp up our operations with terahertz light scattering, where we are able to see things that you would see with green light in colloids. We have had quite some fun with rheology from the simulation, experimental and theoretical side. And coming from the session yesterday morning, it's a no-brainer that in situ resource utilization may need a lot of knowledge for, about, and with granular media. And just to wrap up with a little bit of data, so terahertz light scattering is around 100 micron, which is the frequency, basically giving you length scales that are tailored for granular distances. We did quite some interesting measurements, figuring out that the coffee that we used was clumping, and appreciating our chairwoman. When she was still in Cologne, she measured beautiful curves where you could always not distinguish between the theoretical fit and the experimental data. And I remember when it all started for me, almost 20 years ago, ESA just shut down the planning for building a rheometer in space. And I'm confident that we now have new ideas and may be able to build a proper rheometer for the moon and maybe for an intermediate microgravity platform. Thank you very much.
Okay, now we have time for a few questions. Please go ahead.
I have, if it's possible, 2 questions. One is for the last part, is just more a curiosity. In the terahertz scattering, you measure the intensity of the field. So is it possible, this is the question, to measure the field for terahertz radiation?
Yeah, so what we do at the moment, we try both.
Okay.
We started to measure the field, and I'm really excited doing that.
Okay. And the second question is related to the curve that you show when you apply the piezo. And the question is, you are measuring in a sort of echo mode, so you are able to synchronize the photodiode or the camera with the oscillation of the piezo, or not? Because typically when you have 2 different instruments that oscillate nominally at the same frequency, but it's not the case, you have at the end a large delay.
So what I did is basically you collect the pictures and then you determine where, from the pictures, where is the point that they swap. So I figured out you can see basically where the agitation happens.
Okay.
And you determine that from the picture, and then you can correlate the parts between that.
Okay.
So if you use the correlation while it is basically changing and agitating, it's a really bad defined stage.
Okay, maybe we can discuss later.
Yeah, but that's the advantage. You can actually remove the oscillations by that way.
That's the point.
So do we have another question before moving on? Okay.
Hi, thank you. Jan Rittweger from the DLR. I must admit, I'm only a medical doctor, so this may be an ignorant question. But you had some, positive G's in your experiment. My question is, couldn't you benefit in some applications from hypergravity, for example, on a centrifuge? It's so costly to go to space. Just to demonstrate whether gravity has an effect and how large is it, more or less?
Yes, we can.
And are you doing this?
Well, there's a soil science approach where you scale things by putting it in the centrifuge. And certainly the more valuable data is going to lower gravity. And we're playing some tricks with the grains we are using. But certainly we are arranging things in a way to benefit mostly from the gravity conditions we have.
Okay, so maybe one interesting comment on this is probably that what you expect in high gravity, if you do the scaling, actually does not scale in low gravity. And I think that's what Matthias was trying to say, and that's also the reason why granular experiments actually really do need to go to low gravity. So, do we have one last question for Matthias and Jan? If not, we will thank the speakers again. And move on to the actually last presentation in duetto by Roberto Cerbino and his mysterious guest,
Fabio Giavazzi,
who will introduce himself. Please go ahead.
So, good morning, everyone. My name is Roberto Cerbino. I come from the University of Vienna, and today's co-speaker is Fabio Giavazzi from the University of Milan. And we are going to tell you a little bit about experiments that are at a very preliminary stage compared to the ones you saw today. And they are supposed to fly it on Flumias, which is a facility that is upon completion now. So what I want to tell you today is our experiment is about sedimentation. So what is sedimentation? I'm pretty sure that by now, also thanks to the previous talk, you all know what sedimentation is. But it's basically the idea that under the action of gravity, things can separate because they have a different density. And of course, one thing that was not mentioned today is that there is a sedimentation equilibrium, which is due to the competition between gravity and diffusion. So it is true that gravity wants to bring things down, but it's also true that whenever you create a concentration gradient, you want to destroy this concentration gradient by diffusion, and that's why we have this very famous sedimentation equilibrium. Now, this is quite important because, when you were in middle school, or even probably earlier, you learned that there is a distribution of air molecules on the planet, and this is actually due to sedimentation. If you go on the Everest mountain, you can't breathe. There is almost no oxygen, and this is due to sedimentation. Distribution of plankton in the oceans, many other phenomena in nature are dominated by sedimentation. And very importantly, especially if we want to go to space, I wouldn't go very happily to the moon if I cannot produce a good wine, and producing a good wine means that you have to get rid of this turbid appearance, and this is done once again by sedimentation. Or another very important experiment is if you want to purify water, and this is something that may happen in a granular environment like the one you were describing before, you want to use again sedimentation. So sedimentation was also a Nobel Prize experiment. Jean Perrin got a Nobel Prize in physics due to sedimentation. So you may think, actually, by the way, I like to always tell this story, is actually the moment where people started to believe that matter is made of atoms. And this was not 300 years ago, it was 100 years ago. So until then, many people believed that matter was not made of atoms, despite Democritus and the Greek philosophers. Now, the point is that by now you think that we know everything about sedimentation, right? So it's so old, we know everything, there's a Nobel Prize. Well, that's not true. So in particular, there is something which is called the Luke-Kalflich paradox. I will tell you a little bit about it. And the idea of this paradox came because people started doing experiments like the one you can see here, where you see this sedimenting sample, and you observe the sedimenting sample from the side. Very naive and simple experiment. Now, if you do that, what happens is that you can study but for instance, by particle image velocimetry, the velocity fluctuations. In poor man language, you're going to look at how the swirls of the sedimenting particles occur, because they're not coming down all together in a nice ordered fashion. They do this kind of chaotic random motion around this overall global macroscopic ordered sedimented flow. And now this is very interesting because theory predicts that these swirls should scale with the size of the container. So you get a larger container, you get a larger distribution of swirls and larger swirls. And so you do the experiment and you discover that this is not true. Or to be more precise, this is true only for small containers. So if you take a small container, then the fluctuations are small, then you increase it, they are large, then you increase it, they are large, but then at some point, this scaling stops. And it stops with a very strange equation that was discovered by Phil Segre and collaborators in '97, and you see that there is a sort of limit to the fluctuation size. So there is a limit imposed by the size of the particles and the volume fraction of the particles. You change these two parameters and you change the size, but the container size does not play any role. So there is a tension, as we like to call it, or people in the field call it a paradox, between theory and experiments. Now, many explanations have been proposed. None of them has found this scaling. Last one was 2 weeks ago. So this is actually an active area of research. People are trying to understand why this is happening, and if they do it, why we don't have to do it. So that's why we decided to do something in this respect. So, and one thing that you need to know is that all the experiments I showed you were done during the sedimentation. So during the transient between the uniform profile and the final state where there is a sedimentation equilibrium. So we decided to start from this sedimentation equilibrium. And so basically the very boring situation where we would expect that particles are in equilibrium and relax by diffusion, by Brownian motion. And actually this is what the reason why Jean Perrin was awarded the Nobel Prize. He basically measured the Brownian motion of the particles in this sedimentation equilibrium. And so you do this experiment and you find this thing. What is this thing? First of all, in this axis, we plot the wave vector Q. So this is a sort of scattering experiment. For those of you who know what I'm talking about, this is a dynamic light scattering experiment in which we measure as a function of the wave vector Q, which is here normalized by the thickness of the container in which we do the experiment. We measure the relaxation rate of the fluctuations of concentration. So this is an experiment that in principle you could do with DLS. Then you cannot do it with DLS. You do it with another technique, which is called differential dynamic microscopy, because what you do, you take your sedimented sample and you look from above, and you take images with a microscope, and then you analyze these images as a function of time. And it's a long story short, this is a sort of dynamic light scattering made with images, with microscopy images. Now, the advantage is that with one experiment, you get several Qs, you get several angles, and you get the several rates. So what you see here is a little bit complicated. I'm going to try to drive you around this, or maybe along this, to be more precise. So this regime is what you would expect. So here in this regime, for the largest wave vectors, small length scale, we find exactly what you would expect in a diffusion experiment. What Perrin found in his experiment, tracking the individual particles, diffusion. So the scaling of the rate with the wave vector is quadratic, and the proportionality constant is the diffusion coefficient. Now, in this intermediate regime, the relaxation of the fluctuations occurs faster than diffusion. Diffusion will be very slow. And there is another phenomenon which kicks in, which is gravity, that increases the speed of relaxation of the fluctuations. And then in this other regime, where the fluctuations are very, very large, again, you recover a diffusive-like behavior, but with a diffusion coefficient, with an effective diffusion coefficient, which depends on the size of your container. Now, how do we know all these things? Fabio will explain it to you.
Okay, I will try to. So, I mean, it's not that particularly easy because we saw a lot of things, but if you have been very attentive, you probably, I mean, this picture is shown now for the very first time in public, but you probably see something very similar in a previous presentation. And actually, it's almost identical. This is a slide that was stolen from Fabrizio and Alberto's presentation. And as you can see, our result obtained in an equilibrium on a colloidal sedimented sample are almost identical to the relaxation rate obtained while studying non-equilibrium fluctuation in a binary mixture under thermal stress. So in principle, the two systems are very different. One is in equilibrium, and while the other one is brought out of equilibrium, but the dynamics of the spontaneous fluctuation seems to follow quantitatively the very same behavior. So very quickly, the origin of this giant concentration fluctuation comes from the coupling between the presence of a macroscopic gradient within the sample that in the case of the experiment presented by Fabrizio and Alberto was due to the imposition of a temperature gradient, which by Soré effect was inducing a macroscopic concentration gradient. There is a coupling between this macroscopic concentration gradient and spontaneous velocity fluctuation within the fluid. And two regimes, in the presence of gravity, two regimes can be observed. Again, for large wave vector corresponding to small scale, the relaxation of this spontaneous concentration fluctuation is dominated by diffusion. Then there is a characteristic length scale corresponding to the so-called roll-off wave vector that separate a lower Q regime, where the mechanism driving the relaxation of spontaneous fluctuation is dominated by gravity. And if you are in a finite-sized container at very low Q, you are also influenced by the cutoff effect imposed by the confinement. And so this strong, very strong similarity between the two experiments, between the two experimental results, give us the idea to try to investigate the sedimentation problem by looking for a link with the problem of non-equilibrium concentration fluctuation that are always observed in a mixture where a concentration gradient is present. And so the working hypothesis being that the finite variance of velocity fluctuation, so the fact that in experiment the predicted divergence of velocity fluctuation is not observed, can be explained by the presence of non-equilibrium fluctuations that arise during the transient process and that impose a cutoff to the amplitude of this fluctuation, which is set by gravity. Now, the idea is then to perform an experiment combining these two observations. So velocimetry to monitor velocity fluctuation occurring during the sedimentation process and observation of density or concentration fluctuation. And experimentally, this can be done by performing simultaneous or combined observation of the sample from the side to monitor this swirl imposed on top of the sedimentation process, and from the bottom or on the top to monitor fluctuation in the local concentration. And so with this setup, one can monitor the interplay between this velocity and concentration fluctuation during particle settings, and in particular to investigate the link between the correlation length imposing a cutoff on velocity fluctuation and the roll-off wave vector ruling the finite size of non-equilibrium fluctuation. Now, the ideal experimental setup to tackle this problem would be the one that provides optical access to the sample both along the direction of gravity and perpendicularly to it. that enables switching on gravity when you want. So in this case, in this way, you can investigate the buildup of the concentration gradient starting from an ideal condition where the sample is perfectly homogeneous. And also, you can monitor the other process, where you have an equilibrium sedimentation profile, and we can switch off gravity and then observe the system relaxing back to the homogeneous case. And what will also be very nice is to be able to tune gravity. So the same sample can be studied both in the Brownian and non-Brownian regime, that is, when gravity dominates over diffusion or the other way around. Now, the good news is that this ideal experimental setup kind of exists, and the best real-world approximation to this ideal setup is the ISS Flumias microscope platform that has been developed by DLR, and we will jointly utilize by DLR and ESA. It's basically a microscope. It's a 3D illumination microscope, which basically enable obtaining images with very good axial resolution, similar to confocal, and is mounted on a centrifuge platform such to impose on the sample an effective gravity within the range between 1G and microgravity. And also, there are two experimental configurations. One is called ABC, which is designed initially for mammalian cell culture, where the observation direction is parallel to the gravity vector, and ABP, which is initially thought to perform experiment on plants, where the observation direction is perpendicular to the direction G of gravity. So the project is still ongoing. This is the timeline of what happened so far. The project is also supported by the Italian Space Agency that is supporting some pre-flight activities. The CDR has been concluded last month, and the next step will be to perform a test campaign on the breadboard in Cologne early next year. So I will just to conclude by acknowledging the contribution of the different team members. So the project is led by Roberto Cerbino at the University of Vienna. There are 2 units in Italy, in University of Milan, and an important pillar in this collaboration was University of Düsseldorf in the group of Professor Stefan Egelaf that sadly passed away recently, and so we are trying to kind of reconfigure the activity to keep on working on this project. So thank you so much for your attention.
So thank you very much for putting us back perfectly on time. Thank you, Fabio. So, which means if we have a couple of questions, we can probably already take them now.
I have a question about the DDM measurement. If I saw correctly, the volume fraction, I suppose the initial one is 0.1.
Yeah.
Means that during the sedimentation, you reach on the bottom of the cell which volume fraction?
Ooh, that's a good question. I don't remember. But it depends on the thickness, of course.
Exactly. So the point is I expect that during the DDM you have a very different volume fraction, concentration, different A, but the vertical resolution of the DDM is the worst cell.
This is a very technical point, a very important one, of course. So in all these experiments, we close the condenser of the microscope to have very coherent illumination, and we work as if we were not resolving the layers. Okay. So basically, we have information from the entire thickness.
Exactly.
So it's an average.
Okay, this is an average for all the Q vector, or you expect that for larger Q vector?
Each Q vector is averages with different depth of focus.
Exactly. So the point is that you saw a different.
I think we should do like Matthias, also enter textbook, because people say that a microscope has a given depth of focus, which is not true. In Fourier space, is different for different.
Exactly. So my point is, a large Q vector, you are average a region
Yes.
of the
Small-
in the
smaller
cell that I don't know where is, maybe in the bottom,
center.
at the center. In the other case, you are averaging for low Q vector
Yes.
all the cell. So do you expect that the difference in the diffusion coefficient that you measure could be also to this different averaging due to the fact that the density is
No.
different? Or if you want, you can repeat the experiment with the concentration, initial concentration of the particle. There is
We did.
1% or less than 1% in
Yes,
order
yes,
to...
we did, and basically the picture is confirmed. But also the second answer to your question is that even for the highest Q, we are averaging basically the entire thickness.
Okay.
About this beautiful possibility of switching on gravity on with the Flumias, I think it will be necessary to account for the gravity gradient and the Coriolis forces, because they might have a systematic bias effect. Because if you go down, all the matter will be deflected in the same direction.
Yeah, I mean, in the ABC, say, configuration, I would expect this to be a minor effect because our cells are very thin. And so when the cell is perpendicular to gravity, I would expect it to introduce minor effect.
But it's a systematic effect that is in one direction on the way if you go with increasing radius and in the other direction when you come back.
Yeah. I mean, I would expect this to be more, obviously more relevant when you do perform observation parallel to the direction of gravity. I mean, this is something that we definitely have to account for, yes. That's true.
Maybe, luckily, Flumias canceled the EBP geometry, so there will not be EBP geometry. So this problem will be minimized by default.
Complication arising from experience from the carousel of SMD. Acceleration, tangential acceleration, will mess up everything. So switching on and off gravity, I mean, it's very nice in principle, but when you try to do it, probably we'll see that you cannot switch on gravity without an acceleration, tangential acceleration, even in the ABC probably configuration, the one in which delta R over R is small, but still you have a tangential component, which at least in emulsions proved to be terrible. I mean, wanted to do details, but tangential acceleration becomes very important when you have 0G, because it's the only acceleration that you have. So it's messing up the system.
So probably we'll study another thing.
Most likely.
Okay. I mean, yeah, very nice discussions that we can start again at 11:30 when we all meet again here. So in 23 minutes sharp to have continue this nice discussion. Thank all the speakers of the morning session again. See you at 11:30.